Well, in this section, as you can see as it's titled, or in this lecture, we're going to be calculating volumes using what's called the disk method. And let me start out by saying that the way this works is we're going to use calculus to take a two-dimensional region, or to calculate the area that is done in this way. We have a region in the plane, and that two-dimensional region we think of as rotating about either the x-axis or the y-axis. And as it rotates about one of those axes, then it sweeps out a volume. It's called the volume of revolution. And so we're going to use calculus to be able to calculate volumes of odd-shaped solids that are created in this fashion. So let's start with the first example. Okay, here's the problem, as you can read. Find the volume of the solid formed by revolving the region. Well, I'm sorry for that interruption. Back to our problem. Find the volume of the solid formed by the revolving the region bounded by f of x equal x squared plus 1, y equals 0, x equals 0, and x equal 2 about the x-axis. And as with problems of geometric nature, like we've seen many times before, we really need to draw a sketch or a diagram of what's going on. So let's draw that sketch. Okay, you can see that I have a sketch. Remember, f of x equal x squared plus 1 is a parabola that starts where that has a vertex at on the y-axis at 1, and so we're talking about this portion of the graph, okay, of the definition. Y equals 0, remember, represents a horizontal line, which is the x-axis. So we have that boundary down below. X equals 0 is a vertical line that is this portion of the boundary, and then x equal 2 also is a vertical line that is this portion. Now this isn't drawn to scale, but it gives us a good enough idea of what this looks like. Now, we're supposed to imagine that solid region, okay, two-dimensional region, and we're going to rotate that about the x-axis. And as we do, it's going to create a three-dimensional solid. Let me see if I can illustrate that. Well, as I tell my face-to-face classes, when I start drawing these things, that if only I would have known that I was going to have to draw three-dimensional objects when I got out of school, I would have taken real art instead of art appreciation. But I hope you can imagine what this rotation causes. You can see what we've got there. Now, here's how we're going to. So it's the volume of this solid. So that's solid all the way through that we want to calculate the volume of. It's this solid we want to calculate the volume of. Okay, but here's what we're going to do. We're going to imagine that one little tiny strip in the two-dimensional shape that we've got over here. So this is kind of like how we would deal, we're thinking about how we might deal with calculating an area. This is an infinitely small strip. Now, infinitely small from the point of view that this width is infinitely small. And so since this width is along the x-axis, then we'll call that infinitely narrow width dx. And of course, the height of that particular strip is given by f of x. That's the height. Okay. Now, as we rotate this two-dimensional region about the x-axis, think about what happens to that strip. Let's imagine it over here. Well, let's say maybe it's roughly in this area, and when we rotate that, just imagine that we're going to get something that looks kind of like this. And of course, okay, we get something that looks like that. Now, let's imagine what that looks like. Let's take that piece and let's pull it aside for a moment. Imagine it creates a disc. It's like a hockey puck is what it does. And so that disc, I want to look at over here, laid down on its side. Okay? So we've got something that looks I'm magnifying it a bit, if you will, so that I have a little bit of whoops. Well, that's okay. Okay. Now, so that's the disc that we have over here laid on its side. Now, the disc that we have in the graph has a width, if you will, of dx. In other words, this vertical dimension right here, this dimension right here, is the dx dimension that we referred to at this time. Okay. Now, this disk also has a radius. So let's imagine, because it's a circular disk, isn't it? In fact, it's a right circular cylinder. Okay, let's imagine this radius. Now, that radius is really this f of x. It's the height of that strip. Okay, it's the height of that strip. So the radius here is actually f of x. Remember, this is a right circular cylinder. And you could look up the volume of a right circular cylinder, but let's talk about the volume of a cylinder in general. Right circular cylinder. So let me draw it a little differently. Okay, this time we're not going to have such a squatty cylinder. This one, the one that we have up there, is really a real short cylinder, isn't it? Almost infinitely short. But here's the way we would calculate that. We'll call this the height. And we'll say that this is the radius. Now, the truth is, to get the volume of something of this nature, we take the area of the base, so we can actually do this with different shapes. The area of the base times the height. Well, in this case, the base is a circle. So it's the area of a circle times the height. Well, an area of a circle, remember, is pi times the radius squared. And in this particular circle, the radius is r. And of course, the height in this case is h. So in general, here, for a right circular cylinder, the volume is pi r squared, whoops, that's supposed to be an h up here, times height. Okay, well, that's where we are. So we know, if you will, that the volume of our little tiny disk, our little narrow disk, Well, let's go to the next page to start this. Okay, so the volume of this infinitely narrow disk of revolution that I've illustrated again here, volume is, this is just a short cylinder, is pi r squared times the height of the cylinder. Now, in this case, of course, the radius depends on the function, how high that little strip went that we rotated. So the radius r is nothing more than the functional value, the y value of how high that strip is that we're rotating. And the height is that infinitely narrow width that we determined that we were going to call dx previously. So that's the volume of one single infinitely narrow disk, or short disk as we lay it on its side. Now, remember what integration is. Integration is a way to add an infinite number of infinitely small pieces, whatever that means. And so in this case, what we'd like to do is add up an infinite number of disks that would be created by having infinitely small widths. And so we use integration to accomplish that. Well, in this case, like I said, we're using integration. So in this case, remember, we have to decide where those disks start. Well, they start at the x value of 0 and stop at the x value of 1. So we're going to integrate from 0 to 1. I guess this is the volume of the solid. And each one of those disks has this volume we just discovered above. See, that's what we set up here. So each one of the disks has this volume, and we're adding up all of those infinite volumes to get to the volume of the whole solid. And you can see there, in this case, we can do some work. The pi, being a constant, can be factored outside of the integral. And the f of x is really x squared plus 1. So what we have here is an x squared plus 1 to the power 2. And of course, we're integrating with respect to x. And so now we just do a little bit of work. This is not a big deal. I guess the easiest thing for us to do would be expand that integrand. That is square x squared plus 1. And when we do, we get x to the fourth plus 2x squared plus 1. And of course, we're integrating with respect to x. Well, that integration is easy for us to accomplish because the integral of x to the fourth is 1/5 x to the fifth. The integral of 2x squared is 2/3 x cubed. And the integral of 1, of course, is x. And so we're evaluating that from 0 to 1. And I'm confident that you can complete that part. So I'm going to tell you that the result we get there is 28 over 15 times pi. Don't forget the pi. And of course, this is cubic units because we're talking about a volume. Okay, well, again, let's kind of summarize, or I say again, let's summarize where we are. The disk method, and I should mention here, the disk method of calculating a volume, when we rotate about the x-axis, that's what we've done here. Okay, in that case, the volume is the integral, we'll say pi times the integral from A to B. I'm going to go ahead and factor out that pi value out. Pi times from A to B of the function f of x squared dx, where of course this is the beginning x value, the A value is, and the B value is the ending x value. Okay, if instead, and I guess we'll look at an example of this in a moment, suppose we rotate about the y-axis. We take that same figure and rotate about the y-axis. Instead, we get a different shape. Well, in that case, the volume would be equal to pi times the integral from A to B. And in this case, we won't have a function of x, we'll have a function of y. So we'll call it g of y. That's the radius of our strip that we're rotating. And that's squared and a dy. And so this would be the beginning y value rather than x value. And this is the ending y value. Now, I will also tell you at this point that it is, in my opinion, it's not really a good approach to memorize these formulas. In my opinion, it's best to memorize the process so that you understand where the formula came from, and you can develop the formula then as you're doing the problem. As you do a lot of these problems, you may recall that, but in the long run, you know, a month from now, you want to still know how to do it, and you may have forgotten the formula, but you should understand the procedure. Well, I've had a little change of heart here when we look at this next example. It's similar, it's based on some of the same parts as the last problem. Let's read, of course. Find the volume of the solid formed by revolving the region bounded by f of x equal x squared plus 1, x equals 0, and y equal 5 about the y-axis. Well, this has a couple of problems about it, because when we say about the y-axis, we're expecting a g of y, not when you're expecting a function of y. And of course, that a g of y would actually be an x value, wouldn't it? See, up here, when we say f of x equal x squared plus 1, we can think of that as y is equal to x squared plus 1. But when we're rotating about the y-axis, you'll see in a moment, then we've got to know, we're going to have a function g of y. And you'll see that as I draw. Well, let me go ahead and just draw this shape. So, that's something. Here's our y-axis. Here's our x-axis. And we've got this parabola, f of x equal x squared plus 1, and we're going to go up to where y is 5. So this is we're going to have this parabola that comes up like this, and and we're also bounding it by the vertical line x equals 0, which is here, and y equal 5 we'll say is about right there. So this is the region that we're going to rotate about the y-axis. Now, if we're rotating it about the y-axis, the little strip we imagine being rotated is going to have to be a horizontal strip. Okay? So we're imagining that whole piece being rotated, but let's think of that one little strip of that. Well, now this is along the y-axis, so that width or that height would be dy. And the distance here, okay, which is going to end up being a radius, that distance is not a y distance, it's an x distance. So we need to know what x is when we do this. Well, it's the distance x. I mean, remember what the information we had. we've got f of x is equal to x squared plus 1, which is the same as saying y is equal to x squared plus 1. But we need to know how wide this strip is, that is, how big is x. And so we have to solve this for x. Well, we could do that by subtracting 1 from both sides, and that would be y minus 1 is equal to x squared, but I'd prefer to get the x's to one side here. I mean, the x is on the left side, because that's what I'm solving for. And so from here, we know we can say, oh, well, x would have to be plus or minus the square root of y minus 1. But the part of the graph we're looking at, the x values are positive. So we can comfortably say for this problem, x is the square root of y minus 1. And so this is that g of y, if you will. That's something that we're going to need in a moment. Well, let's imagine what happens when we do this rotation. Okay, so let's imagine what's going on here. Here's our x-axis. Here's our y-axis. And where we are up here, when we rotate this, let me make me a few points that I can refer to. When we rotate this, we're going to get a shape that's going to be three-dimensional, and it's going to be kind of like a solid bowl that's not flat on the bottom. It's kind of it's kind of like a solid bowl, isn't it? And it is a solid because we're looking at solid. There's no holes in what it is we're rotating. Now, that particular strip that we rotate, imagine what that's going to look like. It's going to be, let's say, here's where the back is, maybe here's where the front is, but it's a strip that's being rotated. So we're going to have a disc that is already laying on its side, isn't it? So when we look at that disc above, well, if we could calculate the volume of that solid disc. So that's what we want to know, is what's the volume of this tiny disc? And then to get the volume of the solid, then what we end up doing is integrating, okay, and we have to figure out from where to where, but we're integrating the volumes of the discs. See, we're going to add up all those volumes to get the entire volume of the disc, of the solid. So take a bunch of little volumes, add them all up using integration, that gives us the volume of the solid. So we need to know what the volume of the discs are. Well, let's come back over here. Okay, so here's a representation of that disc that's laying on its side. Now this time, that height, remember, is a dy. See, it came from right over here. That height is a dy. And the radius this time is an x value. See, how long is that x? It's an x value, which is a square root of y minus 1. Okay, now, okay, so the volume of this disc, remember, is the same way we calculate volume of a right circular cylinder. It's pi r squared times height. And in this case, the r is the g of y value. See, it's g of y. It's the x value, actually, isn't it, squared. And the height, of course, is the dy value. Well, g of y is nothing more than a square root. So this is pi times the square root of y minus 1. That's just the x value. That's that radius squared dy. And, of course, that can be simplified even further. That's pi times y minus 1 dy. So that's the volume of one single disc. So the total volume, the volume of the solid is an integral. Okay, we're integrating all these little tiny pieces, but we've got to know where to start. Now we're integrating with respect to y, so we've got to figure out where these disks start. See, they start low and move high. So they're moving, the disks are moving vertically this time. And this low position, we have to know where that value of y is, but that's when y is 1 right there. And so we said we were bounded by y equal 5, and so this position up here is where y is equal to 5. So our solid disks that we're adding up volumes of, the disks start when y is 1, and they stop when y is 5. And so that's the volume that's the way we're going to calculate the volume. Well, we ought to be able to do this pretty easily. We can bring out that pi. And then we can easily integrate y with respect to y. That's nothing more than 1/2 y squared. And minus integrating 1 with respect to y is nothing more than y. And we're evaluating that from 1 to 5. So let's see what we've got here. Pi. Oh my goodness. Let me go offline and calculate this. Okay. Certainly what we're going to have is 1/2 times 5 squared minus a 5. Putting in the 5's first, subtract 1/2 times 1 squared, or y is 1, minus a 1. Well, I calculated this offline, and I got 8, and of course pi. 8 pi cubic units. Okay, we're going to do another example of going back to rotating about the x-axis rather than the y-axis, but I want you to know that you could rotate appropriately about the y-axis. Well, I got a little ahead of myself before I refresh my memory about the next example. We're certainly going to rotate in a vertical way, but it's not going to be about the x-axis. You'll see here. Find the volume of the solid formed by revolving the region bounded by f of x equal 2 square root of x, y equal 1, x equal 1, and x equal 4 about the line y equal 1. So we're rotating about a line y equal 1. See, the x-axis is the line y equals 0, isn't it? So we're doing this a little differently. Well, let's draw the diagram and see what I've got here. Oh, I'm sorry that that's not very straight. Act like it is, please. Okay, so here's the x-axis, here's the y-axis. Let's see, let's assume this is 1, this is 2, this is 3, and this is 4. Likewise, this is 1, 2, 3, 4. Now, f of x equal 2 times the square root of x when x is 0 would be at this point, wouldn't we? And when x is 1, y would be 2. So we're actually at this point. And when x is 4, 1, 2, 3, 4, y would be 2 times the square root of 4, which is 2 times 2 or 4. So we would be at this point. Okay? So the graph, I kind of have an idea of what's going to happen here anyway. The graph, remember, this function is going to come along like this, and then it's going to be here, and it's going to go out here. But I'm thinking ahead because it's also bounded by the vertical line x equal 1. Well, the vertical line x equal 1 is there, so I'm not interested in that dash stuff that I put in there previously. And the vertical line x equal 4 is over here. Okay, it's over here. That's where x is 4. But I also already got ahead of myself because it's also bounded by the line y equal 1. Well, y equal 1 is along here. And so I didn't really need this little extra piece I put in here because this is the region that we're going to be rotating. Now, what are we rotating it about? See, this is where y is equal to 1. We're rotating about the line y equal 1. So not about the x-axis, about this line right here. Aha. Well, let's think before we do the rotation. We're going to, since we're rotating about a horizontal line, that means we're kind of rotating vertically, aren't we? And so let's imagine a representative strip that is vertical in nature. Okay, so there's a representative strip. Now, because the width of this representative strip is along the x-axis, then we call this width, once again, dx. It's infinitely small. But now we're interested about the height of the strip because that ends up being the radius. See, what is this height? Well, we'll come back to see this, but that's the radius. Well, notice that the height of this strip, and I'm using words I probably shouldn't use right now, but all the way up to this level is f of x. But we've got to subtract the part that is below that line y equal 1. So that's 1. In other words, this distance, this is 1, and this level up here is the y value. So we're taking that highest y and subtracting that lowest y, which is 1, but y is f of x, okay? So this amount is actually 2 square root of x minus 1. That's that distance that we've got right there. Make sure you understand that. Now we're going to rotate this about the line y equal 1. Let's see what that looks like. Okay, we get a figure that looks kind of like this. Now this is the line y equal 1 that we rotated about. Oh, I see that I'm a little skewed here, aren't I? Really, I went too far below because this would really, okay, I apologize, it would really come down here and it would be more like this, okay? Now, I apologize for my bad figure. You kind of ignore this part, okay? But hopefully you get the idea. This time it's kind of like a solid bowl that is flat on the bottom, and that's what if we were to put that left side, think of that as the bottom. Now, let's imagine this solid strip that we have over here on the left, and think about what it would look like if we rotated that. Well, now, see, this is the strip would be right in here someplace, see, and as we rotate it, then what we're going to end up with is something that looks like this. Okay, this little strip that we rotate. Okay, of course that's the back of it. But now that's a solid strip. See, that's solid. And of course it's more rounded than I've shown on the top and bottom. It's more rounded. So what we want to know is the volume of that little disc. The strip, when we rotate, creates a volume, creates a disc, and we want to know the volume of that disc. Well, once again, let's lay that disc on its side. So we've got something that looks like this when we lay it on its side. Okay, I'm not trying to be perfect here. Good thing is, because I'm certainly not. And I'm not trying to be to scale exactly. But the height of this right circular cylinder of this disc is that dx, because we laid it on its side. And remember, the radius of this right circular cylinder, or this disc, is the distance that this creates right here. It's the distance, the radius is this distance right here, And how does that compare? Oh, that's the distance we're talking about over there. And so that's the reason we know that it goes up as high as f of x, but it doesn't go down any lower than the y value of 1. So that's the high y value, subtract the low y value, and we have already seen that that's 2 root x minus 1. So the volume of this disk, okay, the volume of this disk being pi r squared times height. In this particular case, that's pi. Our r is 2 root square root of x minus 1, 2 root x minus 1, and that r value is squared, and our height is our dx. So the volume of the solid well, what do? We add up the volumes of all these disks. Each disk has a volume given by this, and how many of those disks are we going to have? Well, an infinite number of them. That's the reason integration is at work. But the disks start when x is equal to, oops, not 0, but 1. Excuse me, when x is equal to 1. See, the disks start at that x equal 1 value, and they stop, here's 2, 3, 4. And actually my 4 was in there, you just couldn't see it. So that's how far the disks go over, and that's related to this 4 right here, isn't it? Okay, so we integrate from 1 to 4. Well, again, we can bring out the pi, and as we expand the 2 times the square root of x minus 1, we actually get, oh, my bad, I'm sorry. We're integrating from 1 to 4, and let's expand this 2 square root of x minus 1 all squared. When we do that, and you can go over and verify this yourself, you'll get a 4x minus 4 times the square root of x and plus a 1. So that's a matter of doing this part right there. Now, as we do that integration, there's our pi. As we do that integration, we'll get 2x squared minus 8 thirds times x to the power 3 halves. Remember what we're going to do when we're integrating square root of x, we're going to change that to x to the 1/2 power. And that's how I came about this. I didn't do that in my head, I'll tell you that. And the integral of 1 is x, of course, and we're evaluating that from 1 to 4. So in this case, that all evaluates to the number 43 over 3. And so our final answer we would write as 43 over 3 times pi. 43 over 3 is, oh gosh, what is that? That's almost 15, isn't it? Not quite. Actually, it's 14 and a third, I believe. It's 14 and a third times pi. Anyway, in cubic units. So a little twist on this one. Now, in the next part of this section, in this lecture, we're actually going, I'll break it into another lecture actually, but we're going to talk about volume of revolutions again, but something called the washer method. So we'll go on to the next page to begin that.